This video is for Lab 9, which is building an audio amplifier. The audio amplifier you need to build for this lab is not a power amplifier. That'll be the next lab after this one. What we're doing is just building a pre-amplifier or a low power amplifier suitable for driving an earbud. So your task for this job is to do the entire design from beginning to end. You will start with just the electret microphone, which you characterized in Lab 7, and a loudspeaker. Except for, because we're not doing the power lab yet, we can't drive the large loudspeaker that you characterized in Lab 8. Instead, what you'll be going to be working on is a little, maybe I'll use a different symbol for it, a little earbud. And there's not one included in your lab kit because we assume everybody's got some sort of earbud. And your goal is to produce an amplifier with adjustable gain that can go from the microphone to the earbud, producing a signal that's loud enough and that you can adjust to make it comfortable. You'll also be using this same amplifier as a preamplifier for the next power amplifier design. And so you'll need to make the gain such that you can get close to rail-to-rail performance when you don't have the load of the headphones or earbuds on there. Okay, so what things do you have to think about? Well, when you characterize the DC characteristics of the microphone, you realized that it needed to have a DC bias on it. What DC bias are you going to put on it? How big a signal do you get when you're using that DC bias and the sort of loudness that you have in the room? So you have to calculate the sensitivity. Then you have to figure out what is the sensitivity of your earbuds. Now, we don't have an easy way to measure that since we don't have any accurate sound measuring equipment, but you can usually find the specs for these, and in the book I've given the specs for one pair of earbuds that I happen to have. I got the specs just from Amazon when I bought the earbuds. So you need to figure out how loud you want it to be, how big your signal is, so how big does the signal have to be coming in here? And the loudness of this is usually expressed in terms of decibels, sound pressure level, and that's going to depend on the power. And so usually the specifications for headphones or anything like that will give you how loud is it at a particular power level. And so you need to figure out, well, what's the impedance of this thing so you know what voltage you need to get that power. Also, because you have a DC bias on the microphone, you don't want your amplifier to amplify that DC bias. So somewhere in here you're going to have to do a DC blocking filter, a high-pass filter of some sort. And you have to somewhere in there to do something to make the gain adjustable. And there's several different ways to do that. There's several different ways to do the filter. There's even different ways to produce the bias on the microphone, because you can use a series resistor with a power supply, or you can use a transimpedance amplifier like we did for the photodiode or phototransistor. So there's lots and lots of options. This is not the sort of design where there's only one way to do it. You have to come up with your own design, build a block diagram for the whole thing. Make sure you've got all the pieces you need, that you get the gains you're going to need, that you're going to get the DC blocking in there. You're not going to saturate one of these amplifiers with a DC signal before you block the DC. All kinds of things to keep track of. Once you've got the whole design worked out, put it on a breadboard and test it. Once you've got it working on the breadboard, you're going to want to solder the thing up. And what you're going to do is to solder it onto a little printed circuit board like this one. And let me pull this out of the breadboard here. So you're going to be having the op-amp chip. You're going to have the microphone here. I've got it coming into a screw terminal on the side. I've got another screw terminal here that I can either attach wires to, or here I've stuck on double-headed pins so that I can stick it into a breadboard easily. Over here I have a potentiometer for connecting, for doing the adjustable gain. This particular potentiometer is one that you adjust with a screwdriver in the screw here. And that's rather inconvenient for a volume control. So on more recent versions of this lab, we've been providing a potentiometer which has a knob on it that's a little easier to adjust. But you're going to have to get everything you want done in just the 4 op amps that are available on the quad op amp chip. There's rooms up here for resistors. Capacitors can be stuck in various places. Notice that I've got a lot of wires on here. The color coding for the wires here is not necessarily very good. I haven't checked to see that I've been consistent in my coloring the way I should be. But I've also added a couple of single pins here in various places as probe points so that I can easily attach the Analog Discovery 2 oscilloscope to various test points on here. That's not essential, but I've found that useful for debugging. Okay, so I did mention using earbuds. Here's headphones I have. These are Panasonic ones. I forget the model number. And I didn't provide a jack for you to plug this thing into, but you can easily connect up to it with alligator clips. The coating of the 3 parts here, there's a tip, a ring, and a sleeve here. And those are left channel, right channel, and then the common ground. So here I've got it so that it just drives the left one without driving the right one. I could try and drive both in series by clipping onto the ring here. And the difference there now is that I've increased the impedance of this thing so it'll put less load on the amplifier. If you've got 4 rings, a tip, ring, ring, sleeve, that would be the configuration you would have if there's a microphone. And there's actually 2 different standards for the tip, ring, ring, sleeve. It still goes left and right for the first tip and ring. Then you have either ground and microphone or microphone and ground. The ground on the ring is the American headphone jack standard, and the ground on the sleeve at the very end is the Chinese standard, which is the older and actually more sensible standard. But you have to know which sort you have. Though if you're not using the microphone, it doesn't really matter. You can just put your alligator clip on both the last ring and the sleeve, shorting out the mic since it doesn't matter. And then whichever one is the ground you'll be connected to. So it's possible to do it either way. And if you do what I did here of connecting to both the left and the right and having them in series, then again it doesn't matter which is the ring and which is the sleeve for the microphone and ground because you're not connecting to either one of them directly. Okay, so I am going to connect up to this, and what I've got is power, ground. Now I'm going to skip a pin, and then there's my output, and that's the way I have got my 4 pins for the amplifier there hooked up. Now we can look at this thing with the oscilloscope. And I'm going to do this first with this right headphone not connected. It's just sitting here on a wire. So that this is without a load. I'll turn on waveforms, and now I've got the oscilloscope here set up with 2.5 volts in the center, and I'm scanning this thing very slowly, 100 milliseconds per division. That lets me see speech waveforms, just sort of the envelope of them, but I can see how big things are getting without having to worry about, oh, I missed it. It's going past very slowly and I can see it. If I do a clap, that's a very loud sound. You can see I'm going completely rail to rail on a loud clap. But when my ordinary speech, I'm getting maybe plus or minus 0.3 volts or something. So I'm not really getting very loud on this. I haven't got the gain turned up very high. I can adjust the gain on this one, but because of the trim potentiometer there, which is screwdriver adjustment, it's too much trouble to be worth bothering with. Now I'm going to connect up the other side of the headphone here, making sure I'm not shorting out the whole thing. But I'm not going to connect it to ground. I'm going to connect it to my virtual ground, which is that voltage in the middle that this thing's varying about. And I believe that is this pin here. And when I do that, it hasn't loaded the amplifier very much. The amplifier can still deliver the voltage it was requesting. And so everything's behaving about the same. And I can check by finding the headphones here and see if it's working. You can't hear this, but I can, and it's definitely amplifying my voice. So I've got this thing working. It's not distorting the voice. It's producing a nice amplification just like I would want it to. Okay, and that's basically what you need to do for this one. Now, what are the tricky parts? Well, aside from just the overall design, let's turn off waveforms here. Other than just the overall design, the other thing that's going to be difficult for this one is laying it out. How do you getting the thing on the breadboard is pretty easy, but you have to get it working on the soldered board because you're going to need this board over again for your power amplifier. It's going to become a component for you. And that's actually a basic principle of design, is that quite often when you're designing something, what you're designing is a module for something, some bigger system. Okay, so here I have got a layout aid for helping you do the layout of where you're going to put things. What this one does is all the red lines are the things that the printed circuit board does for you. So for instance, VDD here already is delivered to the chip. And it's also delivered to this set of solder holes here and this set of solder holes here. Ground is already delivered to this pin of the op-amp chip and those holes there and those holes there. So you have places to connect to a VDD, you have places to connect to ground. You've got the chip already wired up with power the right way around, as long as you put your VDD and ground in the right places here. There's a place here for that screw terminal on the bottom. There's a place here you can put a screw terminal on the side, and there are 3 holes that you can wire up to, 1 for each terminal of thing. And remember that these red wires here indicate, like on a breadboard, holes that are connected together. So you can't do something like, oh, I'm going to put a resistor from here to here, because it's just shorting the resistor out. If you want to put a resistor, you have to go from this hole to somewhere else. Now, these sets of 3 holes on the sides, here and here, are not dedicated to anything in particular. Like the holes on the breadboard, you can use them for anything you want. So if you needed to do something that says, oh, I need a resistor to ground, one way to do it would be to go from ground here to a hole here, and then you'd have 2 places there for connecting up to the other side of the resistor. Because you're going to need a lot of resistors for most op-amp designs, I put some places at the top here for putting the resistors down flush on the board. So you can put the resistor goes into a hole here that's not shown because it's not one you solder wires to. The resistor goes in to the 2 holes there, and then you have 2 places to connect wires up to. And it turns out that's often enough because you have resistor maybe connected to another resistor. You can just do a very short wire from one to the next, and you still have 2 holes left to connect up that pair of resistors where they're joined to something else. So this spot down in the corner here is for the potentiometer, and the potentiometer that I was using was a rectangular one that fits into 3 holes here. You can get other potentiometers that have the same 1/10 inch hole spacing, but with the knob sticking out the side, and that would be a little easier to work with. But again, there's 3 places you can connect up to each one of these things. And what you do after you've got your schematic all worked out and your circuit debugged is to then try and figure out which resistor positions, where you're going to put capacitors, all those design choices in terms of physical layout by drawing lines on here and saying, oh, I'm going to need a wire from, say, this output to the negative input here, because this is going to be one that I use as a unity gain amplifier. Or I might say, oh, I need to put a resistor in here, so I'll take a wire out to the resistor and from the resistor back to here. Draw all those things on here. Generally, when I'm doing this, it takes me more than one attempt. The first time I do it, I end up with, oh, there's a lot of long wires in here. This is going to be a mess. It's going to be a pain to wire. And I go, oh, but if I swap this op amp and this op amp, then all my wires are shorter. Or if I say, instead of making that R10, why don't I make that R5? And then I can connect over to here rather than long wires across. So generally, layout is something that is an iterative process. You put together one that you think gets everything, and then you look at what are the problems with it, where there's going to be difficulties wiring, where the wire is too long, where do I have a resistor that's sort of really awkward. Or you might say, I've got more than 10 resistors. What do I do? Well, there's other places here where you can put resistors. And if you do the flying resistor trick of having it come up vertically and then the other lead coming down into the adjacent hole, that's not the sturdiest way, and you won't find that done very often on professional circuits, but it works pretty well for this sort of prototyping, and it does take up less space on the printed circuit board. Professional boards don't use through-hole resistors anymore. They use surface mount resistors, which are tiny anyway. There are a couple places on here where I've got capacitor symbols. That's where you can put your bypass capacitors, and I do recommend you at least put a bypass capacitor in this place so that any noise that's on the power supply doesn't get delivered to the rest of the board. And you'll probably want, if you end up doing a virtual ground, you'll probably want to have a capacitor to filter the virtual ground also. And you'll need capacitor for your DC blocking filter. So you're going to have some capacitors on here. There's no dedicated places for capacitors. Just put them between a couple holes wherever it is they need to go. And have fun. This one's perhaps the first complete design, all the way from block diagram through to doing the layout and soldering the thing, testing it, that you'll do. We'll do another complete design later this in the course for the electrocardiogram.